Everybody's had a good dose of caffeine here, although I don't think we'll need it. The next talk should be quite illuminating anyways. So I'll start my introduction. My name is Professor Jim Davis. I'm actually an aerospace engineer, so I have a lot of sympathy for the remarks made about the previous speaker about, you know, conservative engineering and stuff like that. So I quite appreciate that. The place I want to start is with some comments from one of the most famous physicists. This, of course, is the late Stephen Hawking. And early this century, he was asked multiple times, what is the most important scientific challenge of the 21st century? And his answer was inevitably fusion energy. And so that's what we're here today to learn a bit more about. So, Dr. Omar here is an American physicist working at the Lawrence Livermore National Laboratory, and he's a scientific leader of the initial confinement fusion program there. Initially, his PhD was from UCLA in plasma physics, and what is he? He's yes, in kinetic theory and stability of certain perturbations in magnetospheric plasmas. That actually really sounds quite interesting. So he holds the title of Distinguished Member of the Technical Staff, and since 2014, he has been the Chief Scientist for the Inertial Confinement Fusion Program at Lawrence Livermore. So Dr. Hurricane has received numerous honors and awards, including the U.S. Department of Energy E.O. Lawrence Award for National Security and Non-Proliferation, and the American Nuclear Society Edward Teller Award, among other things. And, but the reason why we're here, though, is back in December, if some of us can remember that far back, there were some news items about a major breakthrough, the achievement of scientific break-even in laser confinement fusion at Lawrence Livermore Laboratory. This was a major step forward for the lab, and this is what we're here today to hear about. Professor Hurricane.
Thank you. All right, so thank you for the invitation to speak. The title of my talk, as you can see, is Ignition, Venture, and Gain. Before I get to December, though, we're going to start off about 100 years ago, where this idea started from, at the dawn of the atomic age. Oops. And it was actually in the 1920s and 30s where it was realized that the sun and stars make their energy by fusing hydrogen and thus creating all elements in the universe. Francis Aston, using his mass spectrometer invention, found that helium atoms and other atoms were all, in terms of mass, multiples of hydrogen, or very nearly so. And in particular, the mass of helium was about 4 times the mass of hydrogen. Around the same time, very shortly after, Arthur Eddington made a conjecture based on Francis's observations that all elements in the universe are constituted out of hydrogen atoms that are bound together, like building blocks. 8 years later, George Gamow actually derived the probability formula for a nuclear fusion reaction that people in the field call the Gamow factor. And 10 years after that, Hans Bethe developed the theory of stellar nucleosynthesis, which is a very complicated set of reactions that involve fusing protons to each other to make helium in the sun, and carbon, the CNO cycle, the carbon-nitrogen-oxygen cycle, which is another very complicated chain of reactions that could also power stars. So as we all know, if you go outside, fusion does work. Even if you're a skeptic, the sun does it every day. And so Mother Nature does know how to make this work, but we've had a heck of a time trying to make it work on Earth in any useful way. Before we get into fusion, let's just kind of start with the promise of what you could do if you could make this work. And again, this gets back to Eddington's idea. So you've all heard of Albert Einstein and his E equals mc squared formula. It actually implies that we could make a lot of energy by hydrogen fusion, and Eddington realized this. Again, he saw Aston's measurements, and he realized that, well, it looks like 4 protons can combine together to make 1 helium atom. To get the accounting right, you have 2 protons and 2 neutrons in a helium atom. The nuclear mass carries most of the mass, and so it's basically 4 times the mass of the hydrogen atom. But the masses don't really add up correctly. It's about 4 to 1, but not quite. So there's a difference in mass. If you take 4 protons and calculate what the mass is, and you subtract the mass of the helium atom, there's a very tiny amount of difference in atomic mass units, which here it is in kilograms, almost imperceptible. That difference corresponds to an energy because of that E equals mc squared formula. And so if you now, that's per reaction. If you then take that energy that we call the binding energy and just consider what you could do with 1 kilogram of hydrogen, you find that that's potentially 7×10 to the 14 joules of energy, which is about 18,000 times the average US yearly energy use. So that tiny mass difference is potentially a lot of energy. Okay, so that's what makes fusion interesting. All right. Let's talk about some states of matter. There are actually 4 states of matter. You've heard of most of these. You know about solids. Ice is a form of a solid. It's just generally cold. It has a lattice structure and is not a very common state of matter in terms of the universe. If you add energy to that ice, it melts. You get liquid water. If you add energy again, it becomes steam, which is a gas. So that's 3 states of matter. If you add even more energy to the gas, you can rip apart the atoms. You can take the electrons off the water molecules, and you can break the H2O molecule into separate atoms. And that state becomes a plasma. And it's an electrically charged gas that has a lot of disorder in it, and it has more energy than any of these other states of matter per unit mass, and has a lot of disorder in the atoms. So for fusion, it actually was realized early on that doing fusion, instead of doing it atom by atom, it made a lot more sense to make this state of matter called the plasma to do fusion with. So the reason why that's the case has to do with the fact that the nuclei in all atoms have a positive charge. And as you try to bring these positively charged nuclei close together, here I'm showing isotopes of hydrogen, deuterium and tritium. The reason for that will become clear later. They tend to want to repulse each other. So as you shorten the distance between these nuclei, the repulsive electrical force tends to want to push them away, and it goes up as 1 over that distance. Until, of course, you get them very, very close together, a nuclear radii, and then the nuclear forces take over, and you could potentially get them to cling together in fusion. If you look at the periodic table, this repulsion of these atoms depends on the atomic charge, which is what the Z stands for. And if you look at the periodic table, you see numbers on the periodic table, 1, 2, 3, 4. That's the Z, that's the atomic number. Because this electrical repulsion goes as the product of the Z of the materials that you're trying to pull together and fuse, it's really the atoms that are very low on the periodic table that have any chance of fusing, because the Z associated with those atoms is small. If you look at the high end of the periodic table, the Z is very large. So if you tried to fuse these atoms that have Z's of close to 100, it's a product of 100 squared, repulsion energy, more energy is required to get these things to fuse than it does to get these things to fuse. So the energy cost of electrical repulsion is why fusion actually favors isotopes of hydrogen and atoms low on the periodic table as opposed to high up on the periodic table. And because you have to overcome this electric repulsion, we realize that hot fusion schemes really need high kinetic energy to overcome this repulsion. So you need things to go fast, and that's where a plasma becomes useful. So in a plasma, there's actually a distribution of velocities and energies. So here's a cartoon of atoms flying around in a plasma. The same is true for a gas. And they have a distribution of velocities. Some are going fast and some are going slow. And that average kinetic energy of that distribution defines what we call the temperature. Now this is where we get to Gamau's factor on the probability of creating fusion. The Gamow factor says, well, in order to get atoms to fuse, they need a lot of energy because of that electrical repulsion that I was talking about a moment ago. And it's a lot of energy in terms of kilo-electron volts. When you have a distribution of a plasma, though, most of the energy is down here for a given average temperature where that dotted line is. And as a result of that, it's only the atoms that are going very fast, the ones with fast velocities here, that have any chance of fusing. And it's where this distribution, this tail of the distribution crosses the Gamow factor where most of the fusion in plasmas takes place. And this is why fusion plasmas must be very hot, because we're just trying to get this tail of the distribution of all these atoms flying around to be sufficiently high in energy to overcome electrical repulsion to get this Gamow factor sufficiently high for a probability of fusion events to occur. Okay, so you might say, well, why don't we just use hydrogen fusion since that has the lowest atomic number and the sun does it? And the fact is that hydrogen fusion is far too slow for terrestrial use. So we would all be long gone before much hydrogen fusion takes place. That's why stars and the sun have such a long longevity, is because the rate at which they do fusion is actually very slow. So most fusion reactions on Earth do not use hydrogen fusion. We use isotopes of hydrogen. Deuterium and tritium is our favorite. I'm showing here a plot of reaction rate versus temperature. The DT fusion reaction rate is shown in blue, and an approximation to that reaction rate in this regime around 5 kiloelectron volts is shown in black. The reaction rate basically goes as a high power of temperature to the 3.6 power in that regime. This DT fusion reaction produces a neutron and an alpha particle. 80% of the energy comes out as the neutron. 20% of the energy comes out as the alpha particle, which is also that helium-4 nuclei that we talked about before. People in fusion use those terms interchangeably. Very, very occasionally, 4 out of 100,000 reactions, you don't get a neutron and alpha particle, you get a gamma ray and a helium-5 nuclei. So the advantages of this fusion reaction are that the peak in the reaction rate, as you can see here, occurs at the lowest temperature of any of the known fusion reactions. And the deuterium isotope, which is half the fuel, is plentiful in seawater. So that's why this is attractive. There are disadvantages to the DT fusion reaction, though. The tritium is actually radioactive with a 12-year half-life, so it doesn't exist in nature. It vanishes basically in 12 years, so you have to make it to use it. The tritium is actually made from a lithium-6 nuclei being banged into by a neutron. We call that lithium cracking. And the neutron itself actually causes problems for engineering if you're interested in fusion energy. By the way, since this is in keV, 1 EV is 11,000 Kelvin, which is about equivalent to 11,000 Celsius, which is 20,000 degrees Fahrenheit, just so you know. So this is 5,000 EVs, so very hot temperatures to get any significant fusion going on. You can see there are other reactions on this plot, though. We have DD reactions, we have D-helium-3 reactions, we have p-boron reactions. These reactions are interesting, but you can see for a given temperature, they're much lower than the DT fusion reaction rate. This is log scale, so it's 1 to 2 orders of magnitude lower reaction rate for a given temperature. That means to get these reactions to do anything interesting, we require even more energy to get into our plasma to get something exciting to happen here. There are some people who are interested in p-boron fusion because it doesn't make a neutron, but you can see here it's far, far, far less reactive than any of the other fusion reactions. So what you gain in getting rid of that neutron, you lose in difficulty. All right, so that's interesting. You get more fusion reactions with higher temperatures by putting more energy into the plasma, which is kind of an irony. To get energy out, you have to put energy in. But it's more interesting than that. And it comes back to this DT fusion reaction. The idea that makes DT fusion even more interesting than just the reaction rate being higher is that if we can stop this alpha particle in the fusing region. So if we can stop that alpha particle in the fusing region, we could potentially get heat out of it because it has kinetic energy, and if that alpha particle is stopped, it can give up that kinetic energy to the plasma mass and thus heat it, increasing the temperature. Well, if you can increase the temperature, the reaction rate goes up. If the reaction rate goes up, you get more alpha particles. If you get more alpha particles, and you can stop them, you can get the temperature to go up again. If you can get the temperature to go up again, you can get more fusion reactions. If you can get more fusion reactions, you get more alpha particles. That is interesting. We call that process self-heating, or alpha heating. And it's a feedback process where the plasma starts to heat itself. It's not easy to get this going in a plasma, in a DT plasma. The criteria that determines whether or not you can achieve this feedback state is called the Lawson criteria, and it's something we also term ignition. It's a condition on the plasma pressure, the plasma temperature, and time. And you need a sufficiently high pressure, temperature, and time to get this feedback process to happen. But if you do get this process to happen, it means the fusion heating is the power of the energy per unit time coming out of your fusion heating is now exceeding all the cooling. And if the fusion power exceeds all the cooling, you get this thermal instability where the temperature goes up, creates more reactions, causing the temperature to go up, creating more reactions, and you get a runaway effect that can liberate a very large amount of energy. That's what we're trying to do. Okay, stopping that alpha particle isn't so easy. There are two ways primarily to stop alpha particles in a plasma, again, which is this electrically charged gas of atoms. And it's through size and through density. So here's an example of a DT plasma. Here's a triton, here's a deuteron, there's some electrons flying around. Say a fusion reaction has occurred and we've made an alpha particle. If you have a very low product of density and size, radius, you can see the alpha particle can sail right through the plasma without hitting anything. You're not stopping the alpha particle. However, if you have a high rho r, which you could do either by increasing the density or shrinking the size for a fixed mass of material, you have more atoms per unit volume, and now that alpha particle has a good chance of running into something. In particular, alpha particles like to stop on electrons. So one way to stop that alpha particle and get its heat into the plasma is to create what we call high rho r, high areal density. It's density times radius is an areal density. Okay, there is one caveat to that. You can also add magnetic fields because magnetic fields take charged particles and force them into a spiral orbit. And you can see this spiral orbit, the effective length that this charged particle has to follow is now longer because of the magnetic field than as if you didn't have the magnetic field in there in the first place. So this spiraling nature we call a Lorentz orbit could help stop that alpha particle in a plasma even if it's low density, because it's basically an effectively larger path length for that particle to follow. Okay, so because of this need to stop that alpha particle, and the need to get very high temperatures, it turns out that fusion plasmas actually have a significant pressure. There's a simple relationship between the plasma pressure in megabars, this is millions of bars, density in grams per centimeter cubed, and temperature in keV. So if we examine the pressure of a DT plasma at the density of air, which is about 10 to the minus 3 grams per cc, at 10 keV, where those fusion reactions are significant, and you calculate what the pressure is, you get 7.7 megabars. That's 7.7 million atmospheres, because the pressure at sea level is 1 bar, 1 atmosphere. Okay, so then, well, if you're interested in fusion, you might want to contain that plasma in a vessel, because you want to hold on to it, because you want to do fusion. Well, let's look at the strength of some materials. If you look at the yield strength of aluminum, say you want to get a plasma, hold on to that plasma with an aluminum vessel, the yield strength of aluminum is about 550 bar. That's nowhere close to 7 megabars. If you, well, let's say, okay, well, let's look at a stronger material like stainless steel. If I want to make a vessel that holds on to this plasma with stainless steel, I can hold on to about 2,000 bars, 2 kilobars, nowhere close to 7.7 megabars. In fact, if you just look at the explosive, or the pressure of a high explosive, the typical pressure of a high explosive is about 100 kilobars, nowhere close to 7 million bars or 7 million atmospheres. So the reality of the need for high temperature and this density forces you to make a choice, or the high rho R forces you to make a choice. You could either work with very low density plasma in a very large vessel that can be confined using known materials like aluminum or stainless steel, and actually that's the path that leads to magnetic fusion. Or you could just say, to heck with it, I'm going to let it blow up. And that's what we call high energy density plasma, that it just basically explodes, and that's the path of inertial confinement fusion. We just let it blow up. And that basically is why there is 2 paths to doing fusion energy research: magnetic fusion, which is low density, high temperature, and ICF, which is high density and very small scales. Okay, so these realities kind of lead to much different looking configurations. And the 2 basic configurations are shown here. On the right, we have a magnetic confinement fusion device. This is actually a picture from the ITER in Cadarache, France. It's an engineering drawing, obviously. This is a person. So this is the scale of this device. It's about 14 meters. What it is, and here's the working section. This is where the plasma is. It's a toroidal configuration of a plasma. It's large volume because it's low density, because we're going to try to hold on to a fusion plasma and not blow up. So that's why the scale of this is so large. On the other hand, in inertial confinement fusion, we deal with these targets that blow up, so they're impulsive. And these targets are a very small spatial scale. This target here is about 1 centimeter. Obviously, this is an engineering drawing. This target is shot with lasers, in our case, and blown up every time. It's a tiny volume of fusion fuel that starts off in a cryogenic state, and it forms that high-density plasma. Now, what's interesting about these 2 devices, or these 2 ways of doing fusion, is actually the conditions for getting ignition and that feedback process of self-heating in terms of pressure, temperature, time is about the same in a product. The pressures are different. Again, this one you're trying to hold on to it, so the pressures are only about 7 atmospheres. You're trying to hold on to it for a long time, so the time is long, the density is low. Here the pressures are extremely high. They're about 400 billion atmospheres. The time scales, because it blows up, are very short. It's about 1/10 of 1/1000th of a second. And the temperature regimes that these operate in are only about a factor of 2 different, so more or less the same. But the product of pressure times time times temperature is nearly the same for these 2 techniques. Okay, so that's the last I'm going to say about magnetic fusion, because we're not doing that at Lawrence Livermore. We are instead taking this blowing things up path. So there's a reason for why we like blowing things up. It has to do with the Cold War and the fact that the early ideas for inertial confinement fusion actually came out of the Cold War. So the people who were fighting the Cold War back in the 50s and 60s were trying to test nuclear devices to oppose the Soviet Union. And they did experiments at the Nevada test site, which is in a desert about 60, 80 miles north of Las Vegas. And they created a lot of holes in the desert because they were blowing things up with yields of about 10 to 100 kilotons of energy. Just because that might not mean anything to you, 1 ton of energy is 4.2 billion joules, 4.2 gigajoules. But the same guys doing this observed that I think Theodore Maiman developed the laser in early 1960, and they thought, aha, we're in the business here of trying to miniaturize these nuclear devices because they were trying to put nuclear devices on warheads. They were trying to put warheads on submarines. They realized that if they could get enough compression, we could do microfusion explosions, not for military uses, but for other uses, for research uses. And so about 10 years after they had the idea, they actually published a paper in Nature on the laser compression of matter to super high densities. And that was basically when the field of inertial confinement fusion was made public and born. Although there were people working in Russia and in the United States and probably elsewhere on ICF in secret in the 1960s. And of course here, we're not going for kilotons, we're going for kilojoules or megajoules of energy. All you need to do then is get a target and get a laser. So this is what our target system looks like today. It's gone through many bits of evolution over the past several decades, but this is more or less what our targets look like today. Again, remember the spatial scale here is small. This is about 1 centimeter in length. This is a highly engineered object. And so let's just kind of walk through what the parts of this are. We have a central object, a metal can, which we call a Hohlraum. That's a German word for a hollow room. And inside that target is a capsule with fusion fuel on the inside. So here's a capsule. We use materials like plastic and high-density carbon, which is basically a euphemism for industrial diamond, or diamond. And inside that capsule is a layer of fusion fuel coated on the inside of this capsule at cryogenic temperatures. The thickness of this fusion fuel is about 50 to 65 microns. A micron might not mean anything to you, but 100 microns is the diameter of a human hair. So this fuel layer inside this capsule is about half the diameter of a human hair. The total size of this capsule is about 2 millimeters in diameter. And that capsule is at the center of this Hohlraum. This Hohlraum is held with these arms that are cooling arms. They're actually silicon arms covered with light shields so that infrared light doesn't heat the system up, because we have to have this frozen fusion fuel inside, so we have to keep this whole thing cool. You see there's a tube here, which is how we get the fusion fuel in gas form initially into this target. And then we have shields here covering up electronic sensors. And we have a window in the side of this Hohlraum so we can see what's going on inside. And there's a whole team of engineers and cryogenic scientists who build these targets and who create this DT fuel layer on the inside of this target before doing an experiment. So that's our target. Okay, so now we need a laser. There have been many generations of laser at Lawrence Livermore National Lab and elsewhere. The National Ignition Facility is the laser we use presently. This laser is about the size of 3 football fields. So if you put 3 football fields side by side, that's the footprint of the facility. And what you're looking at is a system of capacitor banks on each side of the facility, 96 laser beams on each side of the facility, starting with preamplifiers, then main amplifiers. These are flash lamp pumped lasers. Those laser beams enter into a set of what looks like periscopes, where the laser energy is deflected with mirrors towards the target chamber. We call this part of the facility the switch yard. And then our target, which is 1 centimeter in size, is at the center of that target chamber. Now this system starts off with 300 to 400 megajoules of electrical energy into capacitor banks here and here. Those capacitor banks are discharged into the main amplifiers. And the laser light passes up and down these main amplifiers about 50 to 55 times, picking up energy every time they pass through the flash lamps. By the time that process is done, we only have 3 megajoules of what we call red light. And that red light enters an optics system that we call the tripler that converts the red light, which we also call 1 omega, standing for the frequency, into green light momentarily and then into blue light. 3 omega light is what we also call the blue light. And it's that blue light that enters the target chamber. By the time that blue light comes through the tripler, we're down to 2 megajoules of energy. And that's what enters the target, the Hall-ROM. So this Hall-ROM basically is shown here in comparison to human fingers, again, to give you a sense of the physical scale. It's about 1 centimeter in physical scale and length, as I said before. It's at the center of this target chamber, which is about 10 meters in diameter. And in order to have a chance of this working, that target is centered at the center of this chamber to within 30 microns of the center, which is, again, about the third the thickness of a human hair. And that's done in the dark, by the way, so it's quite an ordeal to get that centered properly. Okay, so 2 megajoules of blue light enter the top and bottom of that can, which we call the Hall-ROM. That 2 megajoules of laser light is actually converted into X-rays because the lasers are not shooting directly at the capsule that's inside the Hall-ROM. They're shot at the sides of that Hall-ROM to create a bath of X-rays that exposes the outside surface to those X-rays and causes it to explode. The capsule, again, as I said earlier, was about 2 millimeters in diameter, again with a human finger there to give you a sense of the scale. Finally, the amount of energy of that 200 kilojoules of X-rays absorbed by the capsule ends up being only about 20 kilojoules of internal energy delivered to the inside of the capsules where the fusion fuel resides. So there's a huge, huge, huge loss of energy going from the electrical energies that we started this whole thing off with, 300 to 400 megajoules. So much energy we don't even bother keeping track of it that carefully. And we only get about 20 kilojoules into the fusion fuel. So that kind of seems silly because we're wasting all this energy, but the reason why we're doing it is we're trying to get energy density. And that's why this field of physics is also called high energy density physics. We're trying to squeeze as much energy as we can into a very small volume because we want to get these ultra high levels of compression and density in order to have a chance of making this thing work. But most of the energy is lost before it ever gets into the fusion fuel. That's the essential nature of ICF physics. Okay, so let's go through the steps of operation of the target because it's not obvious how these targets work. You can shoot lasers at a variety of different things, but as I said, we are shooting the lasers at the inside of this can called the Hall-ROM. And that way of doing inertial confinement fusion is called indirect drive, because we are not driving the capsule directly with the lasers, we are driving it indirectly by making X-rays. So those lasers enter through the top and bottom of the can through apertures we call the laser entrance holes. Those lasers then hit the can and cause the surface to ionize and produce X-rays in the form of what we call Bremsstrahlung X-rays. We're basically creating an oven of X-rays around this capsule. This bath of X-rays then ablates the surface of the capsule because the X-rays are absorbed by the atoms are stripped of their electrons, and that creates high pressures. Pressures of about 150 millions of atmospheres surrounding this capsule on all sides, and they're starting to push it in. That's the stage where we're absorbing about 250 kilojoules of energy. The reason why it's not the full amount of laser energy just has to do with the fact that the surface area of this capsule is small compared to the surface area of the hull room. So the amount of energy fraction-wise is basically the ratio of the areas. Okay, so that very large pressure then squeezes that capsule inwards upon itself. And as we're doing that, we're basically doing mechanical work on the fusion fuel inside. We call that PDV work as we crush this capsule up. That stage of operation is the implosion. Eventually, this squeezes down to something close to a point of about 100 microns in diameter, again about the diameter of a human hair. You're basically running out of anywhere to go. And as a result of that, the kinetic energy that was acquired during this acceleration inwards is turned into thermal energy at a phase we call stagnation, where the capsule basically can't compress any further. And by that time, we only have about 20 kilojoules of energy that we got into the fusion fuel, because most of the energy was expended trying to accelerate this capsule inwards upon itself. So in order to make this work, achieving these conditions for ignition in particular requires precise control of this design, the laser, and the target parameters. Most of the time it doesn't work. Because it doesn't work right, we have to array our experiments with a variety of diagnostics to kind of see what's going on inside and try to figure out what we need to do to fix it. So on the National Ignition Facility, which is a research facility, not a reactor, we have a variety of diagnostics that measure a spectrum of neutrons coming out of the fusion plasma, which tell us the temperature. Of course, we measure the fusion yield, which is the thing most people are interested in. We get imaging data that shows us how the shell of the implosion looks compared to what we want it to look like. We get X-ray emission coming out from the fusion plasma that tell us the shape and intensity and materials that are fusing through their radiation. We get some of those gamma rays. Remember, the DT fusion very occasionally makes gamma rays, so we can diagnose the duration of the fusing plasma through those gamma rays, and so forth. That gives us a complete picture of how our fusion plasma is behaving. Okay, now we can use those imaging diagnostics and the fact that we measure the temperature to infer a variety of properties like that plasma pressure and other properties inside the fusing plasma, because we know the fusion yield is related to the density, which we don't directly measure, the reaction rate, which only depends on temperature, I showed you that earlier, the volume of the fusing plasma, which we get from the imaging data, and the time duration of the burn, which we get from the duration of the X-ray or gamma emission. So we can solve for density, and we can therefore get the pressure, energy, so forth, a whole bunch of properties in our fusing plasma and figure out whether it's working. So one of the metrics that's very important is gain. And gain is a metric of progress, but the thing is, you got to be careful about gain, because there are actually several different types of gain that are important to ICF. There's something called fuel gain, capsule gain, and target gain. And they have to do with the fact that our targets have nested geometries inside them. So the target gain is a measure of how much fusion yield comes out as compared to the laser energy put into that metal can, the Hall ROM, which is our X-ray oven. So it's the energy out of this volume as compared to the energy into this volume. There's capsule gain, which is the energy out of the capsule as compared to the energy that went into the capsule. And then there's fuel gain, which is the energy that actually made it into the fusion fuel inside the capsule as compared to the fusion yield that comes out of it. The fuel gain is actually the most fundamentally connected to plasma physics and plasma conditions. It's actually the most physically important one. The target gain and the capsule gain depend on the geometry of the design, and there's a somewhat arbitrary nature to them. So we track these metrics and others, and what we see is actually there's been a huge amount of progress over the past decade. So this is a plot of fuel gain versus that product of pressure, temperature, and time, that Lawson-like parameter, which tells us how close we are from ignition. And ignition occurs when we see that fuel gain start to explode upwards very rapidly. So this is the ignited regime over here. Now you heard the press, and the way I was introduced is that there was a lot of press in early December having to do with going from here to here. And that had quite an impact. And that was important scientifically, because we went from being on the threshold of ignition to more deeply into the ignition regime. But unfortunately, some of these details were lost on the press, and that really wasn't the interesting part of the story. The interesting part of the story was not going from here to here, it was going from here in 2012, where things were not working, to here, which is a factor of 5,000 in improvement over the past 10 years. And if you want to hear that story in detail, that's part of the physics talk tomorrow. I'm not going to be able to go into that here. So as of December 5th, however, with this highest performance result, we obtained 3.15 megajoules of fusion energy out of our target, as was shot into the target, 2.05 megajoules of laser energy in, thus giving us a target gain of 1.5. But remember, there are many different gains that we track. The capsule gain was 12, the fuel gain was 160, and that's what's reflected here. None of these gains, being greater than unity, means we made net energy. So target gain greater than 1 is not net energy, and this is something the press, a lot of people in the press got very wrong, because it doesn't count the amount of energy consumed by the facility, which was that 300 to 400 megajoules of laser energy in to the facility. So we have not made net energy from our facility. Of course, our facility was not designed to make energy, it's a research tool. Nevertheless, this is important scientifically. It's just you're not going to be powering any homes with this anytime soon. Okay, so the National Ignition Facility is a national security research facility. And I know most people don't actually care about the national security mission. They're interested in fusion energy. So let me describe quickly what an inertial fusion energy power plant might look like. And it has additional complications. So here's an image of a system that's hypothetical, doesn't exist yet, but clearly people are thinking about how you might use this for fusion energy purposes. Here's our target chamber. You put the targets in the center of the chamber. As I said, in inertial confinement fusion, we blow up the targets every time they make energy. Well, that means you don't have one target sitting there forever making energy. You have to keep resupplying targets inwards. We call that target injection. So you have to take a fabricated target, shoot it into the center of the chamber, blast it with the laser, get fusion energy out. 80% of the fusion energy out comes out in the form of neutrons. Those neutrons hit a blanket of lithium on the outside of that chamber, and because of that lithium neutron cracking process that I talked about earlier, you can make tritium. And that tritium then can be bled off and be used to fuel your your fusion fuel capsule. Those neutrons hitting this lithium blanket also make heat because you're hitting this material with high energy neutrons. You can transfer that heat through a heat exchanger, you can boil water, you can turn a steam turbine, and you can make electricity. So that is conceivably how you would do this. The rate at which you have to do this is very high. Here it's 900 cycles per minute, roughly about 10 times per second. It kind of, the details on how rapidly you have to do that depend on the fusion yield and the gain coming out of this. And there are a lot of unsolved problems associated with this system. So, like I just described, we've demonstrated target gain of about 1.5, but for useful fusion energy purposes, you need at least 40. Most people project about 100. So we're a long way from that. You need this high rep rate system. When we do our experiments on NIF, it basically takes us a week to set up an experiment We aren't doing it 10 times a second. The most rapid rate of experiments on IF is 3 times per day, but most of that time that's not a DT fusion experiment, that's other types of experiments. So you need to enable a system where you can do this high rep rate, shoot these targets in, not have these very fragile targets kind of come apart on you in order to make this work. And so your targets need to survive the injector system. That's unsolved. The targets that we build, I showed you before, that looks like a very complicated system, and there are a bunch of engineers that work on it. They're very expensive. That doesn't make sense for fusion energy. They make sense for research, because each target is over $100,000 for these experiments. So you need targets that are eventually economical to build. The target, you need a target factory that turns out the targets at a rapid rate. Our targets presently are made by this team of engineers, and there's a lot of handwork, craftsmanship involved in putting them together. Ultimately, you also need a high-power laser that can sustain shooting these targets over and over again without destroying itself, because when you shoot a laser, it tends to heat up and it does damage to the optics that are shot into this target. So a lot of unsolved problems exist for inertial fusion energy, which is the fusion energy version of inertial confinement fusion. In general, all fusion approaches have challenges. So this is, again, you take your favorite machine, ICF or magnetic fusion. They're all basically going to need this lithium blanket to recover tritium. They're going to have a heat exchanger to drive a steam turbine. At present, there is no such thing as a fusion reactor anywhere in the world. All of the fusion work going on are really experiments, so it's not reactors, and you should be aware of that. Creating the conditions of the pressure and temperature and confinement time that are needed to get ignition to occur, where you have a chance of getting more energy out than you get put in, is very difficult. It's hard, even for people who are experts in the field, it's hard to have an intuitive feel for how difficult this is. We are basically, on our latest experiment, we're reproducing twice the pressure at the center of the sun and 10 times the temperature, just to get the little bit of gain that we've made. Those are very extreme conditions. So for energy production, we not only need to get more energy out than energy in, but you need to compensate for all the energy used to run the machine. So you need 10 to 100 times more energy out than we've been able to produce so far. You need to perfect this lithium blanket so we actually can integrate it into the device and recover that tritium. The neutron damage, as I said, DT fusion makes a neutron. Machines are made out of metal. Metals are crystalline structures. These neutrons come in and hit the atoms, and they dislocate them. And over time, you basically are destroying your machine as you're trying to make fusion energy. So this neutron damage damages the device, eventually destroying it. You have to throw it out. And it creates low-level radioactive waste. And then the tritium, because it's radioactive, and the neutrons are an ES&H, environmental safety and health issues. So there are regulations associated with handling them that all need to be overcome. Okay, but despite these challenges, there has been steady progress in fusion over many decades. There are many ways to make fusion, and today there are a plethora of concepts that have been tried. And there are a number of people, both in magnetic fusion and inertial fusion, all over the world trying to do something. Each concept has its own pros and cons. There is no magic bullet, and anyone who tries to say they've solved everything, they're just not telling the truth. Fusion is still in its research phase, but the engineering needed for useful fusion is coming into focus now that we've shown something interesting. This past year, I like to describe it as an existence proof of ignition. We've demonstrated that it can be done, and in principle, high levels of fusion gain can be obtained. What we've reported is scientifically significant, but we're still making less energy than the input energy into the device, so the total system. So we're not making that energy. Again, the press got that wrong. Doing my best to correct that. Okay, so let's also reality check. I don't know if anyone's ever looked at their electric bill. Your electric bill is actually more interesting than you think. In the US, our electric bills are reported in kilowatt hours, so 1 kilowatt hour. If you convert that to joules, that's 3.6 megajoules. Okay, I just told you we've spent 10 years and a lot of money making 3.15 megajoules with 2.05 megajoules in, not counting the energy into the device. So that's about a third of a kilowatt hour. The average US household uses about 30 kilowatt hours per day. So we are a long way from practical fusion energy. So this is exciting scientifically, but we're not going to be powering your home or the United States or any other part of the world anytime soon. And there are many challenges that remain, and it's not clear that all the problems are solvable. But we solved one of them, and that's where we are. So with that, I'll conclude. And so thank you.
All right, so there's lots of time for questions here. Yes?
Thanks. I'm wondering if the energy is being larger than 1, if you consider the output energy and for example, the electric energy inside the meter. Is the energy being larger than 1?
Again, the gains, there are different definitions of gain. The gain you're talking about where we...
Yeah, like the 96 liter gains.
So the gain that is needed to compensate for this is about 100 times what we've achieved so far, right? Because we got 3 megajoules out, this is at least 300 megajoules. The gain that's associated with the net gain for the facility is termed engineering gain. So I kind of tend to focus on the physics gains, which is the target gain, the capsule gain, and the fuel gain. Engineering gain, which is not mentioned here, is the net gain as compared to the facility. And so that needs to be a factor of 100 more than what we have presently.
Do you believe that first fusion reactors will be a neutral component for magnetic compression?
Yeah, that's a good question. I think it's a mistake to bet on a race by looking at what a car is in the middle of the race. So just because you're in the front at the middle of the race doesn't mean that car is going to win the race. I don't know. What we think is important is we've actually shown that the existence proof of ignition can occur, and the physics is the same, whether it's inertial confinement fusion or magnetic confinement fusion. So if we can do it, others can do it if they can get to the right physics condition, which is that Lawson criteria that I talked to earlier. But who's going to make practical fusion? I don't know.
Why is the fusion fuel going to thin layer?
Oh yeah, that's an excellent question. Yeah, so there's a whole team that makes this cryogenic layer on the inside of the capsule. It takes them a week to do it. They're impressive set bit of engineering and cryogenics. The reason why we don't just fill the whole capsule up is because it would push back as we try to push it in. And we have to get to very high levels of compression, and if it was full from the beginning, we couldn't squeeze it up. So what we do is we put this layer of fuel on the inside, then we accelerate it inwards, and basically for a very long time you can get it to accelerate to higher and higher velocities. I forgot to mention the velocity we get it to, about 400 kilometers per second. And it's only at that time does it start to push back on itself. And so that's why you need that layer, because you need to accelerate to these very high velocities. If you don't get to those very high velocities, you never get enough energy into the fuel to get it hot enough and compressed enough.
So conversely, if you make the capsule larger, where else do you have more acceleration?
Yeah, actually, and that was if you come to the physics talk tomorrow, that is the trick. We made it larger and allowed it to run in more. And that is what, well, there are a whole bunch of tricks, steps, I should say. But to go from here to here, we made it larger. And to go from here to here, we made it, well, there was a first step, we made it larger to go from here to here, and then we made it thicker to go from here to here. But that's part of tomorrow's physics talk where I go into more detail. Here to here, there were just all sorts of problems we had to solve that are kind of specialized. I'll just say the words. We had to deal with hydrodynamic instability. We had to deal with symmetry control of the implosions. We had a problem with our predictions of how much compression we could get being wrong. We have engineering problems associated with the target quality. And all of that is what kind of took 10 years to drag through solving those in steps to get to where we are today. So, yeah, tomorrow.
You mentioned that there is deformation or some kind of decay to the confinement shell to the nutrients produced in the reactor, right? But then the target itself is confined in some like little capsule. And as that blows apart, does the capsule deal any damage to the structure itself? That it's
No, it's completely vaporized. So if this is your hypothetical fusion machine, which is 10 meters or 20 meters away, the little explosion from the debris of the target, that doesn't have any impact because that's completely vaporized. You just turn it into a gas. It's really the neutrons coming out and hitting everything that's the biggest concern for the structure. Well, for the NIF, okay, this is good. So for the NIF, this is a research facility. We are blasting it with a lot of energy. We expect this facility to survive to about 2040, 2045, and then it's probably done. It's not just the neutron damage that is zorching the chamber, but these lasers. This facility was envisioned in the 1990s. It was built from 2000 to 2009, and this is old technology. These are a lot of laser glass in here, and we're putting a lot of energy through it. We're degrading this over time. Actually, there's a constant bit of refurbishment that has to be done on the laser optics, where we're pulling optics out, looking for damage. If it's too, we can refurbish it in some cases. Some cases we have to throw it out and put new laser glass back in. So the facility is taking a beating. And as we get better at doing the physics side, it's taking even more of a beating. So that determines its lifetime. But this facility was not designed for fusion energy purposes. This was designed as a research facility with national security applications. A modern day facility would use new laser technology, a much more efficient laser than we have presently, which is only about 0.5% efficient. And you wouldn't need all the diagnostics that we have, and you'd have a chamber here that's set up to absorb more of this neutron damage. The professor here is an expert on the neutron damage, by the way.
What fraction of the X-rays is absorbed in the capsule?
About 1/10. It depends.
There's the X-rays I've done every cross-section. So the loss, so about 1/10 of the energy that's radiated from the capsule.
Radiated from the capsule or radiated onto the capsule?
Radiated from the capsule onto the, sort of whatever the whole room onto the capsule.
That's about 1/10. It depends on the geometry of the capsule, basically the surface area of the capsule compared to the surface area of the hull ROM. If you have a large capsule and a small hull ROM, you can improve that efficiency. It might only be like 1/7. But generally, because the capsule is inside the hull ROM has a larger surface area, and it's the ratio of that surface area that determines that efficiency.
You're stuck with the X-ray radiation wavelength so that you can't tune that discriminant.
You can tune it to some degree, but there are other consequences. So we use the 3 omega light in particular rather than the 1 omega light, which would give us more energy, because of a problem that we call preheat. And preheat can be understood. Plasmas are quasi-fluids. You're putting laser energy into this fluid. It makes waves. And the waves in this plasma can accelerate electrons. And much like a surfer surfing on an ocean wave, you can accelerate to very high velocities. In our case, those electrons hit our capsule, can preheat it, and make it hard to compress. That problem gets worse with 1 omega light, the red light. So we convert to blue light because it has less of that tendency. So we can change the wavelength or the frequency of the laser, but there are trade-offs. The hull ROM size, changing the size of the hull ROM compared to the capsule, why don't we make a hull ROM very small compared to the size of the capsule, for example? That way we'd have a much higher energy efficiency of converting the laser energy to X-rays absorbed by the capsule. The problem is we can't control the symmetry if we do that. And if you can't control the symmetry, you might have gotten more energy in, but you've wasted it. The physics behind that, again, is tomorrow's talk. So we actually have to stand the Hall-ROM off from the capsule a fair bit to be able to have a chance of making a good implosion.
So one of the questions of your question about the press, and the press handled that energy bookkeeping incorrectly. How do you deal with that? I actually have to confess, guys that actually got net gain close.
Yeah, no, it's, I would.
Away and I'm like, oh my God,
yeah,
this is amazing.
Yeah.
And I just actually have to understand today.
Yeah, so it's a shame because the scientific advancement is significant. Yeah. And unfortunately, that kind of diminishes the value of the scientific. As you can see, this is fairly specialized, right? It's.
So what did you do?
I cringed, and I kind of sent an email. I sent a career-limiting email to my management, but it's always very difficult. I've kind of learned this dealing with the scientific press when you talk about things, especially like fusion. It tends to get hyped a lot, and I tend to be personally very careful about explaining things. And I go out of my way to explain things that I think have a chance of being misinterpreted. And I do know, again, a lot of the press was saying net energy gain, and it's not net energy gain. And net energy gain is misleading. It is significant because we have made target gain, which, again, is the first time ever anywhere. And you can see this is going up very rapidly now. And that's why, it's not going to take much more to go even higher if we can do it. So that's, the very nonlinear nature is also something that's very hard to explain to non-experts. So anyway.
So having achieved your target gain goal, what are the next physics or engineering goals at?
Yeah, so obviously we want more target gain. We want to keep pushing this as high as we can go. We don't quite know how far we can push it with what we have. So we're trying to further optimize the target physics to squeeze more out of it. We're trying to squeeze more out of the laser system itself because it turns out to go from here to here depends on how much energy we can get into the fusion fuel. So if we can start with more energy out of the laser, there's a very chance we can move to the right or move up this curve rapidly. So the laser engineering team is trying to explore how much more energy they can squeeze out of the laser. The recent result was with, it says it right here, 2.05 megajoules of laser energy. Back here, these were being shot with maybe 1.5 megajoules of laser energy. We went up to 1.9. There's a plan to try to get to 2.2 megajoules of laser energy by the end of the summer. And probably in 200 kilojoules increments, we're going to try to push the laser to 2.7 megajoules. Because we are pushing the laser kind of beyond its design limits, sort of like if you're a Star Trek fan, Scotty, the engineering, she can't take anymore. That's what we're trying to do. We're trying to squeeze as much out of laser as we can until everything breaks, or just before everything breaks, and see how far we can go. The other issue we've had is our targets. These targets, I'll get into more detail on this tomorrow. These targets are complicated. They're man-made. They're highly engineered, but they're not perfect. There's no such thing as a perfect engineered object. And some of the defects that we have, particularly in the capsule, which you can't see here, but I'll talk more about tomorrow, can compromise the way this system operates. And so we're trying to understand the material science and engineering of these targets in the capsules to try to further clean those up and have less impact on the physics. So a lot of engineering and applied science research involved in what we're doing.
Is there any hope at all of having a triple band fusion without a full run?
Yeah. Oh, actually, yeah. So that's a whole, actually, just across your lake here. At University of Rochester, the Laboratory for Laser Energetics, they primarily study what's called direct drive fusion, where instead of shooting the lasers into this Hall-ROM, they shoot the lasers directly at the capsule. There's a trade-off there. The benefit of that is you throw out the Hall-ROM, which is a whole layer of complexity out the window. You can drive a larger capsule, like you intuited, larger is better, because you don't waste, in quotes, or consume the energy in this with X-rays, right? You go directly to put the laser energy on the capsule. You kind of save almost a factor of 10 in energy, and that can be significant. The downside of indirect drive is the way the laser transfers heat into the implosion is not through X-rays, because you're not doing indirect drive, you're doing direct drive. The heat is transferred through electrons, and electrons have a very small mean-free path compared to X-rays. When you have a small mean-free path, it means you're making gradients steeper and steeper and steeper, and there's more of a tendency for hydrodynamic instability with steep gradients. There's also a tendency for not being able to control the symmetry quite as well, because this X-ray oven provides a relatively smooth bath of X-rays to drive this implosion inwards upon itself. But if you're hitting the laser surface with these, the capsule surface with these lasers directly, imagine the surface of a golf ball. You know, you're making all these little divots in it, and that can make the implosion asymmetric. There's a negative energy consequence associated with that. So it's not clear, and this is the way we've done it. It's not because this is the best way to do it. It's just there's one of many alternatives, and this is the one we chose. It's not, don't go away from this saying, oh, indirect drive is the right thing to do because they're ahead right now. From a scientific point of view, there's pros and cons to each concept. And
why not use an X-ray laser?
Excuse me?
Sorry, why not use an X-ray laser?
An X-ray laser? Well, no, what? You know, the guys in Men in Black show up if I talk about that, you know, cart me away and you never see me again. So in principle, you could use an X-ray laser, sure, but you would still have this problem of divoting the surface. And,
Are there theoretical limits on the fuel gain that can be achieved?
Yeah, that's an excellent question. Yes, there are theoretical limits. For DT, it's about a factor of 1600, I believe. The 1600, if you take a ball of plasma, you can get a gain of 1600 for the energy you put into that ball of plasma compared to getting out. The gain you could get out by packing more cold fuel around that is effectively very high. It's like asking, how big of a forest fire can I start with one match? Once you start the forest fire, the fire can spread almost indefinitely if you pack enough wood around it. And
so are we like a factor of 10 away from the maximum?
No.
So this facility kind of reminds me of like the 1970s where, like, you know, when they were developing recent computers and there were rooms full of computers and they were trying to develop a single thing. If this is sort of let's say this becomes the future of fusion energy, if you could redesign, not on a reactor wise, but if you could redesign the facility in a way that maybe gets rid of some of the 1990s level stuff, what kind of changes would you do to it to try to increase the efficiency of it?
Oh, that's a good question. Really, it's not my expertise to talk about what we could do with the facility. Again, we think we can make a smaller, my colleagues who are the laser engineers think they can make a smaller footprint facility using diode pumped lasers and get efficiencies out of the system that are of order 10 or 20% energy efficient. The details of how to do that, I'm not an expert in. This laser is 0.5% efficient, so 0.5% efficiency.
In your DT fuel pellet, is there any heterogeneity in the mixing of deuterium and tritium?
Yes, it's so the deuterium and tritium here starts as a gas, and you put the gas in, you cool it down, and it liquefies, and it forms a puddle at the bottom of this capsule. And then the cryo team basically grows this layer, which is, they try to make it a single crystal ice layer to try to make it as uniform as possible. that doesn't always work out right. And so you'll get heterogeneity in this layer. You can almost, I don't know if you can see it from back there, you can actually see a little defect here. See a little defect there. They're small, but you can get grooves in these capsules where as the ice crystal grows and wraps around, it might form an interface, and you might get multiple crystals to form, and you have multiple interfaces. When you get the magnified images, they look like canyons. You can get bubbles in this ice layer. Not on this scale, you can't see them, but you can get little air bubbles. Also, because the mass of tritium, there's an extra neutron in tritium as compared to deuterium, as this starts to form out of the gas, you can, in principle, get a gradient in the deuterium-tritium ratio on the inside of the wall as compared to the outside of the wall. But we think that's a very small effect. Yeah.
Just expanding on what you were just talking about, what is the manufacturing process for these capsules?
For the capsules, it's made out of a plasma deposition process. So this capsule here, in this particular case, starts life as a plastic ball. You put it into a chamber about this big that has something that looks like a plasma fountain coming out of the top, where you have carbon plasma coming out and flowing down. And the plastic balls are circulated on a tabletop. If you've ever seen like an old record tabletop, it's something like that except turned on its side and has grooves in it. And those plastic capsules roll around in this plasma, and you're building up the capsule surface atoms at a time. So it's like growing an onion from inside out. And that's how you form the capsule. Then, to get that plastic ball out, you drill a hole in the side, and you pour acid in, or you dump it in acid, and that dissolves the plastic, and then the liquid mush of acid plus plastic comes out of that hole in a process they call sonication. So it's a very small hole, and they're vibrating it ultrasonically that sort of shakes out all the slush of plastic and acid, and that's how you get your capsule. So yeah, so that hole that they drill, we just want one hole, that's what we call that's where we put the fill tube. So that they take a glass tube, and these are the same sort of tubes that they use for in vitro fertilization. So there's a company, yeah, it's funny, you take these glass tubes and you draw them out, you draw out the glass to these very fine scales on the order, we started with 10 micron fill tubes. So 10 microns is 1/10 the diameter of a human hair. The latest experiments, we were using 2 micron and 5 micron fill tubes, so really tiny fill tubes that they've been drawn out of glass. And those are inserted into the hole, and they're basically glued in to the hole to hold them in place, and that's how we get the fuel in that coats the inside of that capsule. Yeah, a lot of interesting and weird engineering goes into this.
And you got to do that 900 times a minute.
Yeah, exactly. That's why we're not there yet.
Hi. So my question is, isotopes like helium-3 are obviously very difficult and expensive to come by on Earth. So my question is actually less about energy and just asking, what is the sort of progress that we have towards harnessing fusion products? So where does that fall in the timeline of net energy gain? Is it significantly before?
I'm not sure I understand your question.
So the fusion of, say, helium-3.
Yeah.
Or when will that become, is that an area of research interest?
No, not for us. I don't, my personal opinion is these are not credible for fusion energy research. And I'm not going to comment on any fusion companies in particular, but.
In terms of harnessing energy, but just for the product itself.
Oh, just for the product itself? No, so, yeah. I mean, this consumes helium. It doesn't make helium. It's, this is D plus helium-3. Sorry. This is D plus helium-3. This consumes helium. So, oh yeah, I guess you could make helium out of the DD reaction. Yeah, you can make helium from the DD reaction. We've never really considered that as being that useful, but.
If you read enough science fiction, you'll know that they build colonies on the moon to mine helium, so they can burn.
That's usually what. not just science fiction. But, yeah, that's where most people think you want to get helium from, is mining it from the moon or asteroids.
Yeah. How much tritium do you guys have?
Well, so it's tritium, again, it kind of goes away all the time. So we make it, and actually the tritium that we use at NIF is made at the Savannah River Power Station in Savannah, Georgia, and it's made from standard fission power plants, basically using lithium, like I said. So it's made all the time. You don't want to keep a lot of it on hand because it's an ES and H issue. Yeah. Yeah, you can use, people have, you can use electromagnetic traps and magnetic confinement to hold on to these plasmas, but not at these pressures. So that's all those electrostatic confinement and magnetic confinement devices, they use a very low density, and I mean, many orders of magnitude lower than air. So it would be vacuum, near vacuum to us. So.
Fusion power. So with a name like that, how secure should I be?
Yeah, so it's actually called the National Ignition Facility, NIF.
But it's a national security.
It is a national security. What it is a facility built and funded by the national security apparatus of the U.S. government for primarily national security issues. So
it's fun to try to visit there.
So let's see. I'm trying to understand how secure. Yeah. Oh, yeah. There's definitely a fence around it. Yeah. With armed guards. So yeah. Although tours are available, you have to call ahead, though. From a scientific point of view, I'm just going to go with your question to see if I hit. The purpose of this, again, is primarily because we ended nuclear testing in 1992. Yet, regardless of your politics, and I know there's a spectrum of politics regarding nuclear deterrence, the U.S. has a lot of nuclear weapons. And the people who designed them are nearly all gone now. Yet we still have these things. And we have to make decisions about them a lot. And there are a lot of younger people now who are supposed to be stewarding this stuff. And they use computer models to understand how these things behave. They didn't design the original things. They never saw them actually work. Yet we have them. So the purpose of this is to kind of vet people, vet the computer models that we use to monitor stockpile. Is the physics correct? Is it accurate? And to emulate some conditions that only exist in two places, stars and at the interior of interior stars and the interior of nuclear devices. And it's there to kind of make that system as credible scientifically and grounded scientifically as possible. And then there's the side benefit that you learn about fusion research, and that has a knock-on effect. And, again, it depends on your politics. I think we have these things. It's important to have the best science underpinning the stockpile that we can, as long as we have those things, and have to make decisions about them rather than not. So does that make you feel more secure? I'd rather have good science behind those technologies than not. And
Are there models of plasma physics hold up to the results that we were getting back then?
Excuse me?
Like, how are our models of plasma physics holding up?
Oh, yeah. So, okay, that's an excellent question. And I'll get into that more tomorrow. So, okay, so I guess there's how close were our computer models at predicting what was going on at NIF. And it was, there's a spectrum of results. So the models predicted that we'd be able to get higher compression targets than we actually did. So they were optimistic about how much compression we could get. And we had to change strategies as associated with that. The models are sketchy at predicting the symmetry of our implosions in these Hall ROMs. So they don't get that quite right, which is why we had to do, one of the other reasons we had to do so many experiments. The models are actually pretty good at doing the implosion physics, basically modeling how this thing compresses up and the hydrodynamic instability. And the models are an essential part of designing these experiments. As with all models, and as you probably have learned in your physics classes somewhere, you ever hear the phrase, interpolation is easy, extrapolation is hard? Okay, well, these computer models are imperfect. And if you try to extrapolate from where they are known to work too far, Mother Nature can get you. And you can be off in your prediction. So we've demonstrated that they are useful and pretty accurate if you don't extrapolate too far from where they've been kind of calibrated to things working. But if you don't do that, things can turn out much differently than you expected based on the models. And that's an important part of the learning, and that's kind of gets back to that, how secure should we feel. Learning that and having a new set of people learning that lesson is important. Yeah, so we can see the symmetry by looking at these images. So at stagnation, when we've turned all that kinetic energy into internal energy, and the temperatures have gone up and the densities have gone up, as it's doing the fusion, it's getting really hot. So it emits X-rays that we can look at it with. That's these sets of images. And then those neutrons, those fusion neutrons that come out, they hit the cooler material on their way out of the capsule, and they scatter. And we can measure those neutrons and see an image of what they're scattering off of here and here. And they basically see, hey, it was supposed to be round. This isn't round. It's dense on top, dense on the bottom, not dense in the middle. It's a little squished. It's not round. We've got to fix something.
Is there a preferred axis for the asymmetries? Is it aligned with the Hall ROM?
Well, yeah. So this one, if the z-axis is vertical, so with the Hall ROM. So this is actually a pretty common asymmetry, where we have density on the top and density on the bottom. We have less density on the side. It's a little squished, which we would say it's oblate, not ideal. As again, kind of in the physics talk tomorrow, that lack of being perfectly round is a direct reflection of kinetic energy of the implosion that never made it into making the fusion fuel hot. And there's an interesting relationship there. And that basically means we've wasted some of this energy that we put in, but we hardly get any energy in, so we can't afford to waste it. So that's how we do it.
All right, I suggest we thank our speaker.
Yeah, thank you.